Okay, BC Calculus. So we're going to move now on to a thing called continuity that we're going to discuss that has to do with limits. So you're going to see that. Oh, that's a little better. And we're going to see some different limits and our first super specific definition. There's going to be times when you need to know a definition for some part of calculus very, very specifically, and this will be one of those times. So it's kind of theoretical on this. There'll be a little bit of practical, but it'll be mostly theoretical stuff. So first question, here we go. When I say f of x equals x cubed is continuous for all real numbers, but g of x is not continuous, then what do you think that word means? That word continuous means. And I'm not going to write an answer here. You could take a second. What do I think continuous means there? And I hope people just have the idea of connected. You know, the continuous means it's connected, and not continuous means there's a break somehow. And that totally works. That's totally true in terms of what continuity means in the idea sense. But now let's talk about it. We need to make it more precise than that. You know, how can we tell if there's some unusual function? And we'll show you one in just a little bit where how do we tell if something is continuous if it's kind of a weird function? So here's a definition of what it means to be continuous at a point. We're going to start with that and just say we're not going to talk about a whole function being continuous. We're going to say let's talk about a function, and we're just going to say it's continuous at one value. And what things would you need to have there? Well, it's going to be continuous at a point x equals c. So let's think about this. So we've got some curve, and we're at a point c. And what do I mean when I say that it's continuous? And here's the specific definition. One thing is that the limit as x approaches c of f of x equals a number. The limit exists. So you have a limit right there, and that would be the thing that's getting closer and closer to. And so you've got a limit. You have to have a limit at that point, otherwise you do not have continuity. The second thing is that f of c also gives you L. So not only is there a limit, but also the function is defined, and at that point it has the exact same y value. And then it's implied from the statement before, so this is not extra, but it's that the limit and the y value are the same of f of x equals f of c. So what you get when you get close to c is the same thing as what you get when you plug c in. So that's the specific definition. So we're tying the definition of continuity not to this general idea of connected, but to limits existing and being the same as the y values themselves. Right? So I already drew your picture. So in practical terms, the way people think of continuity, and you can put this down, I'll just say it, is if you can draw it with your pen without lifting your pen from the page. So if you can draw the function and your pen doesn't lift up, then it's continuous. That's like in practical terms. Now let's talk about what does it mean to be continuous on an open interval. So if we've got some function, and I'll let you know, I always, when I say, oh, let's just draw a function, I always tend to draw them exactly like that. I need to get some variety in my random abstract functions. So what do we mean by being continuous on an open interval? What we mean is from A to B that it's continuous at every single point. So is it continuous there? Yes, because the limit equals the y value. Is it continuous there? Yes, because the limit equals the y value. But notice this is over an open interval. Okay? And the reason why it's tricky is because the endpoints are tricky for the interval. And we'll talk about that now in just a second. Here are some examples. Give an open interval that is continuous for that function. Give two reasons why that one is not continuous. And then calculate the values of c and d that would make it continuous. The first one I'm going to answer, and then I'll write out an answer for the second one on a pause. So any open interval that didn't include 0 is an answer for the first one. So I don't know, 3 to 4. That's fine. 1 to 8, negative 100 to negative 2.7, whatever. As long as you didn't include 0, you're good. Now, this one's kind of interesting. Two reasons why f of x equals sine 1 over x is not continuous. Now, one thing you can do is, the easy argument is that f of 0 is undefined. Remember that you have to have a y value at the point. That was condition 2 up above. And so you have to have f of c being that limit. And so, and f of 0, if you plug 0 in, it's undefined. So it can't be continuous. Now, if you graph this, it gets kind of interesting. I need to get a virtual calculator. But if you graph it, then what you'll notice is that it looks kind of normal when you're zoomed out. But if you zoom in closer and closer and closer, like if you go from, and I'm going to be making up these numbers, so no guarantee it's exactly right. If you go like from negative 0.01 to 0.01, that's me showing the x scale. And we go from negative 2 to 2 because it's a sine graph. And so sine goes from negative 1 to 1, and that gives me a little border. Then what this graph looks like, and you might need to zoom in more for this, is it looks like it's, it's coming along and it's coming along, and then it gets closer and closer and closer and tighter and tighter and tighter together. And then it does the same thing on the other side. Whoa! And then it starts slowing down. What's happening here is that when you plug in x values that are fractions, 1 over x turns them to big numbers. So like when you're plugging in 1 over 100 for x, then 1 over x turns that into 100. And when you plug in 1 over 1,000 and you're getting really, really close to 0, that turns it into 1,000. Basically what you're kind of doing is you're taking, this is just going to be weird, you're going to take the whole normal sine graph, the sine graph, and you're compressing it and squeezing that infinitely long sine graph into this little area right here, because you're using the 1 over, and that turns the big numbers into tiny, tiny little numbers. The result is there are infinite oscillations between negative 1 and 1. So it's going up and down and up and down between negative 1 and 1. That was my top and my bottom there. An infinite number of times in that little space right around 0. No matter how close you get, as long as you've got an interval including 0, an open interval, then you're going to see an infinite number of oscillations. You're going to see there's always infinite oscillations. Even if you get closer, it's still doing this. So, well, why is this important? Well, that means there's also no limit. Limit as x approaches 0 of f of x does not exist. There's no limit. The limit does not exist between at 0. There's no limit at 0. So if it fails both of them, the funny thing is when you look at the picture, it looks like it's connected. You say, well, it's all looks connected. I can't see a break because it's a weird thing, this infinite oscillations. So you can see how this is an example of one that's kind of confusing because you're doing these infinite oscillations, and then at 0 it's kind of a mystery, and then you're doing infinite oscillations there too. The one thing I could say is, remember the description of using your pen, like if you can draw it with your pen. Well, you couldn't draw this function with your pen because if it has infinite oscillations, you're going to run out of ink. That's my useless but oddly funny way of looking at why this is not continuous. All right, now calculate the values of c and d that would make this one continuous. I'm going to pause it and I'm going to write it out. You could pause it too right now, and you have a chance to check it out and see what you think the values of c and d are. So try to figure those things out that would make it connected. Okay, finishing up. So I worked out the value of c by plugging 0 into this function and 0 into this function, because in theory I need the two of them to give exactly the same value as an answer. Even though 0 doesn't apply to the second part, the second rule, I still need it to be like, well, if you kept going, that it would get closer and closer to 0, to the same thing as 0 as you get from 0 on this side. Make sense? Okay, that was very poorly said, and I apologize. So I need both of them to give me the same answer at 0 so that they're continuous. And so I just plugged in 0 for x and solved for c. Then I had c, and I did the same thing for the second two functions, but this time I need them to give the same value at their border when they transition, so I need to give the same values at x equals 1. And so I plugged 1 in to both the second rule and third rule using the c equals 1/2 thing from earlier, and I solved it from there. And I got the value of d, and I checked it on my calculator and graphed them and made sure they connected. Now, one thing to notice here, a little sort of AP thing right now, is you might have noticed that this was my expression here that I came up with. One thing that's true about the AP test on any free response that you're writing is that you're not required to simplify. I'll repeat that again. You're not required to simplify on a free response question. And that'll be true for us too, as long as I don't say something in the question. I'll have to say, simplify your answer. And then there must be some algebra thing I want to review there and see that you can do it. But otherwise, you do not have to simplify any expressions. So that answer right there is totally fine. Technically on the AP, if you write, if your answer is 1/2 and you say x equals 2/4, that's fine. That's an acceptable answer. This would be for C, excuse me. I was just giving a different answer for C. If you said -2 over -4, technically that's fine. If you say C is equal to -1.9 repeating, I'm sorry, not -1.9 repeating. I need to do 1 over. No, 1 over 1.9 repeating. There we go. Yes, technically this would be accepted. I will say, the graders try to be incredibly fair. I'm an AP stats grader, and they try to be very fair and very objective, and they try to follow the rubric. But if I saw something like that on a test, I'd think to myself, wow, that student's trying to be deliberately obnoxious. And I can't promise that my heart and my grading mind might be led astray by my annoyance at the student doing that. So I try not to let that affect my scoring, but I couldn't promise it. I do my best, but that's all I could do. So don't be obnoxious with it is all I'm saying. But just know that you have some weird, complicated expression, but that's your answer. That number is your answer. Leave it. Move on with your life. Okay. Next up, so a little tricky problem here. So if you look at the definition of continuity and you were intuitive, what would you say is the largest interval for that function? And I'm saving time. I just wrote it'd be 0 to infinity. I mean, that's what square root x looks like. It looks like 0 to infinity. The problem is it's not continuous at 0 because the limit doesn't exist at 0. Right? You can't approach from both sides. We've said that. To have a limit, you have to be able to approach from both sides. You can't approach 0 from the left. There are no function values. So therefore, it's not continuous at 0. But this seems kind of silly, right? I mean, you look at it in terms of having this word be expressing something, and you could say, well, boy, it seems like at 0, it's continuous, like this whole thing is continuous here. So yeah, the rules are kind of a pain to us. What we're going to do is in the second video, we're going to look at what needs to be, how we can modify our rules so that we can say it's continuous at 0. But this is a good time to take a break. So I'll pause it and we'll come back and we'll expand our definition of continuity so that we can deal with this kind of situation.